All right, here we go. This is problem 116 out of chapter 4 of the Halliday and Resnick textbook. So we've got an elevator without a ceiling, and it's ascending, moving up at a constant speed of 10 meters per second. So the velocity of the elevator with respect to the ground is 10 meters per second in a positive j direction. A boy on the elevator shoots a ball directly upward from a height of 2 meters above the elevator floor. So the position of the ball with respect to the elevator initially is 2.0 meters in a positive j direction. Just as the elevator is 28 meters above the ground. So the vertical position of the elevator with respect to the ground at time 0 is 28.0 meters in a positive j direction. I guess I don't really need to keep track of all these j's, right? Everything's going to be vertically, so let's not even worry about all these j's. Okay, cool. It says the initial speed of the ball with respect to the elevator is 20 meters a second. So the velocity of the ball with respect to the elevator initially is 20 meters. Oh, I guess I should, 20 meters per second. All right, there we go. So that is all of our given information. All right, so A says what maximum height above the ground does the ball reach? So I'm trying to find the height above the ground, so I want to do everything relative to the ground. All right, so here's what I'm going to do. So relative to the ground, the velocity of the ball relative to the ground initially, well, that's equal to the velocity of the ball relative to the elevator initially plus the velocity of the elevator with respect to the ground initially. It's constant, but we can put it in there. So for us, that's going to be 20 meters a second plus 10 meters a second, right? 20 meters a second plus 10 meters a second. Well, that's just 30 meters a second. All right, and then we want to know how high it goes. Well, at its highest point, the velocity of the ball relative to the ground is going to be 0. Oh, and we know the acceleration of the ball with respect to the ground. It's negative 9.8 meters a second squared, and it's a constant acceleration. So to find our displacement, here's all we're going to do. One of the equations we learned was this guy, 2a delta x equals vf squared minus 2a delta x equals v squared minus v naught squared. So plug in your numbers. Let's see. You get 2 times negative 9.8 meters per second squared times the displacement equals v squared, which is going to be 0 at the top, minus 30.0. No, I guess we don't have 0.0, just 30 meters a second. Don't forget to square it and solve it. And your displacement turns out to be 75.9. No, it doesn't. It turns out to be 45.9 meters. I almost goofed there. All right. So, but that's the displacement above the point where the ball is released, right? So that's the vertical displacement with respect to the ground of the ball between the instant it's released and it reaching the top of its path. But at the instant it's released, it is 28 meters, well, at the instant it's released, the ball is 2 meters above the floor, and the floor is 28 meters above the ground. So add all of this up, and you get, I'm out of room, 75.9 meters. All right, so that is part A. All right, so now let's do part B. All right, to do part B, what we're trying to do is we're trying to figure out how long it's going to take the ball to return to the elevator floor. So now we're worried about the floor of the elevator. So everything here is going to be with respect to the elevator. So here's what we know. Within the elevator's frame of reference, we know that the velocity of the ball initially is 20, well, I guess I should do with respect to the elevator. So the velocity of the ball with respect to the elevator initially is 20 meters a second. I know that the acceleration of the ball with respect to the elevator, because the elevator is moving at a constant velocity, is negative 9.8 meters a second squared. And I know that since it was released from an initial position of 2 meters to hit the floor, it's got to go down 2 meters, right? So our change in position of the ball with respect to the elevator is negative 2.00 meters. All right, and you got to find the time. So there's a couple of ways of doing it. A lot of people tend to jump right into this guy. We know everything there, right? We know our, oops, sorry, VO, not VI. So we know everything in this equation. We know our acceleration, we know our displacement, we know our V naught, and you got to find the time. But solving that requires that you use the Pythagorean, not the Pythagorean theorem, sorry, the quadratic formula, which, as I've said in class, I don't care for. So we're going to do this a different way. I'm going to use that same equation I just used a minute ago. So 2 times the acceleration times the displacement is equal to V squared minus V naught squared. So all of this is ball relative to the elevator. So I know everything here except for the velocity. So let's find the velocity the ball has when it hits the ground. Okay, so I'm going to get 2 times negative 9.8 meters a second squared times, it's got to go down 2 meters. That's got to equal V squared minus 20 meters a second squared. And solve that, and your velocity ends up being negative 20.96 meters a second. Okay, so we're almost done. So now what we're going to do is this. We're going to say, all right, well, I know that time is V minus V naught over A, right? So my V is negative 20.96 meters a second. Oh, I should notice I had to put this negative in manually. You take a square root, and then you just need to think about, oh, well, it's moving down when it hits the ground, so that velocity is negative. All right, so anyway, that's why this is negative, minus our initial velocity was 20 meters a second, and our acceleration is negative 9.8 meters a second squared. So solve for your time, and you do, in fact, get 4.2 seconds. All right, there we go.